Hey everyone, my name is Aurora, and my partner Alicia and I will be discussing our project today. We will be in Euclidean geometry, and we will be discussing the parallel projection, which is in chapter 11, more specifically, section 11.3. So to begin this video, we would like to just recall a few different definitions, theorems, and postulates that will be of great assistance in the proof of the parallel projection. So let's get into it. So the first definition we begin with is the definition of parallel lines. So this is something we covered in chapter 9, and the definition is as follows. So it says, let K and L be two lines. We say that K is parallel to L, denoted like this. So K is parallel to L if the intersection of K and L is equal to the empty set. So now this proof is crucial in understanding the proof of the parallel projection. And just as a little spoiler, there's going to be lots of lines, and some are going to be parallel, while others may not necessarily be parallel. So keeping this definition in mind will definitely come into play, as you will see later in the video. So the next theorem that we would like to recall is also from chapter 9, and it's theorem 9.3. So this is just a theorem that says parallel lines do in fact exist. So it says, let L be a line and P a point not on L, then there exists at least one line K through P that is parallel to L. So yet another spoiler of the video, we will see that the parallel postulate that was discussed in more detail in the first project is basically, so this theorem 9.3 is in fact like a less defined version of the parallel postulate, because the parallel postulate states the same conditions that L is a line and P is a point not on L, but in fact the parallel postulate says that the line through P and parallel to L is unique. And here in 9.3 says that there exists at least one line through P that is parallel to L. So again, we find in the parallel postulate that the line through P and parallel to L is unique. So again, this is also going to be useful later on in the proof of the parallel projection theorem. All right. So the next theorem we will call is, again, from chapter 9. It's theorem 9.7. More specifically, there's 3 parts of this theorem. We include the third part just because it is a part of the proof of the parallel projection theorem, which is like the big theorem that our project is about. So basically, this says if K1 and K2 are parallel lines and T is a transversal, then there exists a pair of congruent alternate interior angles. So right here in this picture, you kind of see K1 and K2, they're parallel, and T is the transversal. So the alternate interior angles, well, there's actually 4 of them, but we included just a pair of them, which is gamma and alpha. And so you see, in fact, that they're 59.48, which is congruent to the same value as alpha. So let's move on. The next, so we're going to jump like a few chapters back. We were in chapter 9 for a majority of these that we were recalling. But we move back to chapter 3, which is the ruler postulate. So the ruler postulate basically defines the distance function and a bijection. So it says that there exists a function d, which is u times u onto r, which is called the distance function, such that any line L, there exists a bijection c, where it's L onto r, with the property that the distance of A and B is equal to the absolute value of C of A minus C of B for all points A and B on L. So again, of all the theorems that we have recalled so far, this is probably the most useful one. I keep saying this, but like as you will see in the proof of the parallel postulate, we use this heavily, specifically in case 2, where we partition our line AC into n equal parts. I know this may not make sense like right now at this point in the video, but using the ruler postulate is a main idea as to like how we can partition the line segment AC into n equal parts. For now, it's just important to understand like this is going to be important. Alrighty. So just one more postulate and one more theorem to recall. So in chapter 11, we've seen these two things, the parallel postulate and Proclus's theorem, discussed more thoroughly and in depth in project 1, but we just want to relate it back because it does play actually a major role in later on in this video. So the parallel postulate basically says that, like I was saying, it's a more specific and has the uniqueness property that actually theorem 9.3 lacked. So basically it's the same condition. So if L is a line and P is a point not on L, then there exists a unique line K through P and parallel to L. So again, this uniqueness factor right here is extremely important. And then again, we have Proclus's theorem, which says that let K and L and T be distinct lines. So we have K, L, and T, such that K is parallel to L and that T is not parallel to K. Then that would imply that T is also not parallel to L. So T would intersect L at some point that's right here. Or it could be like over here, depending on where T is. So Proclus's theorem and the ruler postulate like kind of give us like a concrete foundation to the proof of the parallel postulate, just because this is how we can get our lines to be constructed in a way that allows like to more clearly see like what's going on in what a parallel projection is, and more over how the proof goes. All right, so now we're going to jump into a new definition. So this definition is the parallel projection from K to K prime using T. So this looks like a bit of information. So let's take it kind of piece by piece. All right, so let K and K prime and T be distinct lines such that T intersects K and K prime. So right here, we have our line K and our line K prime. We have our line T. Moreover, we define a mapping from K to K prime. We think of T as a direction and project the points from K onto K prime using the direction T. So this is kind of what's going on here. So we let A be a point on K, and then again, by the parallel postulate, we know that there exists a unique line, let's call it TA, through A and parallel to T. So then again, since T and TA are parallel, and K prime intersects T at some point, then we have that TA also intersects K prime in a point, let's name it A prime. That's from Proclus's theorem. And so moreover, that's how we get our points B prime and C prime, where we see that B prime is created from T being parallel to T prime. And then again, we have that K prime intersects T. So then we have that TB intersects K prime at a point, let's say B prime. Moreover, the C would be similar, except we would use TC and T. And then again, K prime would intersect T. And then by Proclus's theorem, we let this intersection point be called C prime. So moreover, we can define this more specifically by using a map. Let us call this map pi. So pi would be the mapping from K to K prime, such that A goes to A prime. Moreover, B would go to B prime, C, C prime, and this would go on forever. So basically, this is the definition of a parallel projection from K to K prime using T as both a direction. So that was a lot, but basically, T is our direction. we get our points A prime, B prime, and C prime using both the parallel postulate and Proclus's theorem, and we just define this as a map called pi. All right, so now we can use all the definitions, theorems, and postulates which we have just discussed to understand and walk through what the parallel projection theorem actually states and the proof of the theorem, which is, like I've been saying, is the big theorem in our section in chapter 11, which is actually theorem 11.19, which is in fact the parallel projection theorem. Alrighty, so let's get into what it says. So before we get into it, we're noting that the parallel projection also preserves ratios, which is in fact what the theorem kind of says. So let's read the theorem. So the parallel projection theorem says, with the above notations in definition 7, which definition 7 is this one, which we just discussed, is the parallel projection from K to K prime using T. So we have all of this. Basically, this is our image that we were working with. So with the above notations in definition 7, let A, B, and C live in K such that A, B, and C, the B is between A and C, holds, which is exactly what we have here. So if this happens, then the distance between A and B over the distance between AC is equal to the distance between A prime and B prime over A prime, C prime. Moreover, that the distance between A and B over B and C is equal to A prime, B prime over B prime, C prime. All right, so let's get into the proof now. So recall that definition 7 actually gave us this image, which is the same one that you just seen on 2 slides ago. So we begin with letting K, K prime, and T be 3 distinct lines, such that A, B, and C live in K, and moreover that B is between A and C, so A, B, C holds. So we want to show that the ratio of the distances between A and B over AC is equal to the ratio of distance between A prime, B prime over A prime, C prime. Moreover, the distance between A and B over B and C is equal to A prime, B prime over B prime, C prime. We want to show that both of these hold true, right? So notice by definition 7, since we have that B is between A and C, because we just showed that it's a mapping from K to K prime using T, we also have that A prime, B prime, C prime also holds, moreover that B prime is in between A prime and C prime. So to begin our proof, we're first going to prove 2 special cases of the theorem. So we begin with case 1. So let us suppose if the distance between A and B is equal to the distance between B and C, then this would imply that the distance between A prime, B prime is equal to B prime, C prime. So then again, the picture that we're working with is this one that we have seen multiple times so far. All right, so we have 2 cases, and let's take the first subcase of case 1. So we're first going to assume that K is parallel to K prime. Then again, we have 2 quadrilaterals, namely A prime, B prime, B, and then the second one would be B prime, C, which, by the definition of a parallelogram, these 2 quadrilaterals would be in fact parallelograms. So then again, this means that the distance between A prime and B prime would equal the distance between A and B. Moreover, the distance between B prime and C prime is equal to B and C. Then again, from our assumption, because we assumed that the distance of A and B is equal to the distance of B and C, which yields that we just found that we can just replace them. The A prime, B prime is equal to B prime, C prime holds as well, which actually this is what we wanted to show, right? So we have the distance between A and B is equal to B and C, which implies the distance between A prime and B prime is equal to B prime, C prime, which is in fact what we just got. So subcase 1 is done. So now subcase 2 actually gets a little bit more interesting, per se. So next we assume that our line K, which is this purple line, is not parallel to K prime. All right, so they're going to intersect at some point. Then again, from the parallel postulate, we can construct a few lines. So namely, let's begin with K double prime. So K double prime goes through a point A prime, which is parallel to K, right? K double prime is parallel to K. Then again, by Proclus's theorem, we have that K double prime will intersect TB. Again, TB is from our definition 7. This intersection point is going to be B double prime. So then again, similarly, we can construct D triple prime, where D triple prime goes through a point B prime, which is K triple prime is parallel to K. Then again, from Proclus, we can have that K triple prime will also intersect TC at a point C triple prime. Then again, here we note that the lines K double prime and K triple prime are not equal, so they're two different lines. This image is kind of just a recreation of what we were working with. I just decided to put it into GeoGebra just because it's easier to see the different lines and different colors and what's kind of happening, rather than just having the picture all one color, and it's kind of more confusing. Anyways, all right, so then again, similarly to subcase 1, right, where we have the distances between A and B is equal to the distance of A prime, B prime. In our case, right here we have that the distance between A and B is equal to the distance between A prime, B double prime, right? And the distance between B and C is equal to the distance between B prime and C triple prime. Yeah, so that's from, so we assumed that the distance between A and B is equal to the distance of B and C. And then from our two, from these two cases, which is where we found them from subcase 1. So we can just, again, plug and play here because they're both equal. And so we get what we wanted, right? Or not necessarily what we wanted, but it will help us in the way. Sorry. So anyways, so then again, we notice some triangles form from our lines. We notice like a few of them, right? But specifically, let's focus on triangle A prime, B double prime, and triangle B prime, C triple prime. All right. So in these two triangles, we have that K double prime is parallel to K triple prime. Then again, that's because they are both parallel to K, and we just seen from project 1 actually that these two would also be parallel. So we let K prime be the transversal between K double prime and K triple prime. So we notice a few angles that are formed, right? So we have B prime, A prime, and B double prime, A prime, and B prime, and C triple prime, B prime, and C prime. are corresponding angles, right? So that's going back to the theorem part 3, right, where it says that we have corresponding angles, right? Okay, so this basically means that these two angles are actually congruent. So we have the green angles, which are B prime, A prime, and B double prime, A prime, and B prime is congruent to C triple prime, B prime, and C prime, which again, those are our green angles. So using a similar argument with the two parallel lines and the transversal, and then you get corresponding angles that are congruent. We have that TB is parallel to TC. Then again, where K prime is acting as our transversal, we get that B double prime, B prime, and A prime is congruent to C triple prime, C prime, B prime, right? The angles between those points. So this would be, in fact, the red angles, right? So we found that these measures are the same, these angles, these green angles are the same, and these red angles are the same. Which from all these, we can actually conclude that the triangle A prime, B prime, B double prime, and B prime, C triple prime are in fact congruent. That's from our angle side congruency theorem, where we have the red angle, the green angle, and then this segment A prime, B prime. Over here we also have the red angle, the green angle, and then the segment B prime, C triple prime, right? So then again, using CPCTC, which gives us that B prime, that gives us that A prime, the distance between A prime and B prime is equal to the distance between B prime and C prime. Again, CPCTC gives us that because this is the segment of the triangles, for lack of a better words, between the red angles and the green angles, and then it's between the red angles and the green angles. So then again, these two would in fact be equal to each other. So this actually concludes the first case of the theorem, which then again, just going back, our first case we wanted to prove that the distance between A and B is equal to BC implies that the distance between A prime and B prime is equal to the distance between B prime and C prime. So we took the case where K and K prime were parallel. We saw what happened. And then again, we took the case when K and K prime were in fact not parallel. And we used the parallel postulate and Proclus's theorem to kind of construct different points and different triangles and kind of seeing like what that led us to, which in fact it gave us exactly what we wanted. So this concludes case 1, and then Alicia will take over with case 2, where you see something more interesting than again using the ruler postulate.
Okay, so now we're going to look at case 2, which is when AB is not equal to BC. So then we let there be some rational number Q that represents AB over AC. And then we are trying to come back to the bigger picture and show that AB over AC is equal to A prime B prime over A prime C prime when this is some rational number Q. So again, we're letting Q be some rational number. So that means Q can be represented by two natural numbers, M over N. And then we are going to apply the ruler postulate to partition our segment AC into n many equal segments. The important part in this is that they're equal segments. And so this is just the picture that we had in the book. So we have A to B. If we look at these segments that is divided into as kind of one unit, then we can be AB is represented by 2 units, and then BC is represented by 3 units. So that kind of represents what we're showing here, is that AB and BC are not equal. So then when we're drawing this, we can rename the points at these segments where those parallel lines are intersecting line K as A0, A1, A2, all the way to AN. In our example, we defined our n to be 5, but hypothetically it can be n many segments. And so you can see where these new points are represented on this line. There's a naught, a1, a2, a3, a4, a5, and so on. Again, all of these are intersecting at our line K. And so just like how the picture shows. And it's also important to note that a naught to a1, a2, a3, so on and so forth, all the way to an also holds. So they are in order as shown on this line. It's also important to note that AC is divided into segments of equal length, as I highlighted here. And so we see that the distance from a naught to a1 is the same distance as it is from a1 to a2, a2 to a3. Each one of these units is exactly the same. And this can go on all the way from a sub n minus 1 to an. Here, again, our n is defined as 5, but it could hypothetically be all the way up to n. Then we also have this formula, a naught to a1 is equal to a1 to a2, so on and so forth, all the way to till we get to the last 2 points, would be a sub n minus 1 to an. And overall, this distance from each defined point is the same distance as the segment AC divided by n, which is clear to get since AC is divided into n many segments. Then clearly this would be AC divided by n. So in our given segment, we define our a naught to equal a and our an to equal c. And then we can take it a step further and create this new formula from a to any ai, where I is any number from 0 to n, is equal to I over n AC. So for example, coming back here, if our I was 2, so we're going from a naught to a2, or from a to a2, then the formula is saying that a to a2 is 2 over 5 AC. We know AC is 5, so we'd get a to a2 is 2, which is correct. So we have, building off of that last slide, then we previously defined our AB over AC to be n over m. So with some algebra, we can move this around. We multiply the AC to both sides, and now we have AB is equal to m over n AC. And then plugging this into this formula right above here, we see that this m is just replacing where the I is, and so we get m over n AC is equal to a time, or the distance from a to am. Which is equal to AB. So we have AM is equal to AB. And then coming back to this bigger picture parallel projection, this is exactly what it would project to on the opposite side. So we have our A naught prime, A1 prime, A2 prime, A3 prime, A4 prime, and so on and so forth. So we also have that for any I all the way up to n minus 1, this holds. Then we have that this same idea holds, this AI minus 1 is equal to AI, which is equal to AI plus 1. It's exactly here. It's just showing that as long as they're directly next to each other, the distance between each segment is going to be the same. So as we proved in case 1, which is when AB equals BC, if this is true, then it is also true for those prime values. So then we have A naught prime and A1 prime is equal to A1 prime, A2 prime, so on and so forth, all the way up. And so we get this same value again, is that A prime, or this this distance from each individual segment is 1 over n times A prime C prime. So we come back full circle, and we have A prime B prime is equal to this, since we had defined that here, that B is equal to AM. And so we get M over N AC. So then that implies that our A prime B prime over A prime C prime is equal to MN. And we defined right in that beginning of this part of the proof that MN is AB over AC. So we see that when AB over AC is a rational number, then A prime B prime over A prime C prime is equal to AB over AC. Okay, so now we're going to take a step back and generalize this idea. So we're not saying that we're working with a rational or irrational number, kind of like what we were doing up here. We're not saying that AB is equal to BC or that they are not equal. So we just take a step back to generalize our entire proof. So we suppose by contradiction that a prime b prime over a prime c prime is less than ab over ac. Then we know from number 3 that there's some rational number q such that q lays between a prime b prime over a prime c prime and ab over ac. So then we are fixing our q, and then we can choose some point D. We do this by segment construction. We can choose where this D lies. So we choose our D so that AD is equal to QAC. And then we can manipulate this to be Q is equal to AD over AC. And then coming back to this, this equation that we have here, we can manipulate it, and then we have that AB is greater than QAC. We get this just kind of at multiplying AC. So then we have AB is bigger than AD. Since AD is equal to QAC, we plug that back in right here. So AB is greater than AD. And if that is true, then we also know just from in betweenness that ADBC holds. So we know we know from our definition above that if ADBC holds, then A prime, D prime, B prime, C prime also holds. So then we take a step back. So since ADC holds, then we have, as we had defined above, A prime, D prime over A prime, C prime is equal to AD over AC. And again, we know that our Q is equal to AD over AC. So similarly, since A prime, D prime, C prime holds, we know that in the bigger picture, we have A prime, D prime, B is right in between here. So we know that A prime, B prime over A prime, C prime is greater than A prime, D prime over A prime, C prime. And then since this is equal to Q, then A prime, B prime over A prime, C prime is greater than Q, which is a contradiction to what we had assumed here. So since this is a contradiction, then we know our assumption is wrong. Thus, its negation is true, which is A prime B prime over A prime C prime is greater than or equal to A prime, or I'm sorry, is greater than or equal to AB over AC. Then I'm going to go ahead and just kind of go through this a little bit. I'm going to go ahead and just skip through this, this second part. What this is basically showing the reverse, where we are supposing that A prime B prime over A prime C prime is greater than AB over AC. And then it's the exact same proof as what we had just went through here, but we just switch pretty much all of the primes and the not primes, and then switch a couple of the inequalities. And then we'll get another contradiction. So this is true. So then we know if A prime B prime over A prime C prime is greater than or equal to and less than or equal to AB over AC, then they must be equal to each other. Then building off of this, we can use some algebra to get the second half of our theorem, saying that AB over BC is equal to A prime B prime over B prime C prime. So this is just the algebra. We can kind of go through it super quick. We're manipulating it. We're dividing this AC. We're breaking it up into AB plus BC, and then just cross multiplying, and then we see our AB times A prime B prime cancels out, and then we get back to AB or AC is equal to A prime B prime over B prime C prime. So we prove both cases where AB is equal to BC and when AB is not equal to BC. And we showed that for some A, B, C, and K where A, B, C holds, then AB over AC is equal to A prime B prime over A prime C prime, and AB over BC is equal to A prime B prime over B prime C prime.
So now that we have covered the proof of the theorem, let us recap what we discussed today and kind of give insight into what the next project will discuss. So today we discussed the ideas of the parallel projection from K to K prime using T. Again, that's from our kind of lengthy definition in the beginning. And we also discussed the relative definitions and theorems to assist in our understanding of such projection. Then again, we also discussed the parallel projection theorem, discussing both what exactly is that, and then we showed the steps of the proof for it, taking both case 1 and case 2 and the subcases, and looking at what our different scenarios were. And then we kind of got it to where we wanted it, which is that the ratios of distances are actually preserved through parallel projection. And again, that's what precisely what our theorem of a parallel projection actually states. So this is where our discussion was actually brought to an end. And this kind of leads into the next topic, which is in chapter 11 as well, and it's 11.4. And what's going to be discussed in there is the idea of similar triangles. So then again, thank you for watching our project, which was on parallel projection.